Hello there again. We're going through balancing chemical equations in this video. If you want to see the different types of reactions, I did that in one of the review packet videos, so you can tune back into those for a refresher on types of reactions. Let's focus on a double replacement reaction first, where we take, let's say, lead to nitrate plus potassium iodide, and it produces something. Well, lead and potassium are both metals, so they can swap places with each other. We start by writing symbols. Lead will now be partnered with iodine. I'm not finished with this, but I'll come back to it. And potassium will now be partnered with nitrate. Now we check our oxidations. They won't be part of our final formulas, but we'll check them here. So we've got lead was a +2, we know from over here. Iodine's a -1, potassium's a +1, and nitrate's a -1. This formula is done because it's balanced. This formula is not because this 2 needs to come down here. So now that we have the correct chemical formulas, we can balance the equation. And what that means is we're going to have to add coefficients in front of it. Now, we're adding coefficients because if we change the subscript, for example, if I made PBI instead of PBI2, that's not a compound because lead was a +2 when it went in, and iodine is a -1. This thing would have a charge of +1. Compounds have a charge of 0. Therefore, this is not a compound. So the subscripts do not follow their elements necessarily. Now you might be going, wait a second, that 3 followed the O, and that's because NO3 is a polyatomic ion. It moves as a group. Unless it's broken apart, if you see NO3 on both sides, then you can assume that it's survived the reaction without breaking any of those bonds. It's simply moved as one giant unit. And so that 3 is part of the symbol for nitrate, just like that B is part of lead's symbol. You can't just write P for lead, because that would be phosphorus. You can't write NO for nitrate, because that's nothing. That's nitrogen monoxide if it's a compound. Or NO2 becomes nitrite. It's a totally different ion. So keep the 3 on the polyatomic, but that 2 did not follow it through because the potassium is only a +1. So the balancing, the easiest way to do this is to do an inventory. Once you have enough practice, like in the other video, I just went through and did this by looking at it and changing a few numbers here and there. But if you do the inventory, we set it up so we've got lead going in. We have nitrate on both sides, so I'm going to write NO3 instead of N and O. That makes things a lot easier. We're going to write potassium, and then we also have iodine. You start the inventory by counting how many go in. Leads, there are only 1. Nitrates, there are 2. Potassiums, 1, and iodines, 1. Coming out of the reaction on the product side, we have 1 lead, 2 iodines, 1 potassium, and 1 nitrate. And so in this particular reaction, there's no one place that's better to start than another, so I'm going to just randomly choose to do the nitrate, and I can make 2 nitrates come out by putting a coefficient of 2 in front of potassium nitrate, the only chemical product that has nitrate in the formula. So now I have 2 times 1 nitrates, so I change this to a 2, I update, and then I do the same thing for potassium because potassium is also affected. So 2 times 1 potassiums. Notice I've unbalanced potassium, but that's okay. We'll come back and we'll fix things later. Alright, iodine, 2 come out of the reaction, but just 1 goes into the reaction. So I can stick a 2 in front of potassium iodide, and my iodines will now balance. 2 times 1 is 2, 1 times 2 is 2. So those are balanced. And here's why we can just skip some things and come back to them later. Potassium has just sorted itself out without us needing to do anything separately. When I put that 2 over there for iodine, it also gave me 2 potassiums on this side, which now balances out. Everything that's left over, because these are all balanced, gets a coefficient of 1. And so this particular reaction, I don't think I can zoom out any further, I'll just slide. This particular reaction has the coefficients of 1, 2, 1, 2. And they can occur in any order. So if I wrote the potassium iodide first, it would be 2, 1, 1, 2. And I could flip these in any direction. It does not matter. Okay. Let's look at another double replacement reaction, except let's do an acid-base neutralization reaction, which is a kind of double replacement that's a little special. So let's say you take sulfuric acid, aqueous hydrogen sulfate, plus, and let's choose magnesium hydroxide as our base. I'm going to get the products by combining hydrogen with hydroxide, so HOH plus magnesium with sulfate, Mg and SO4. Well, plus 1 minus 1, HOH is good to go. Plus 2 minus 2, magnesium sulfate, good to go. So now we balance this equation. I'll do it by the same inspection method here, where I'm going to write down the symbols for everything. So we have hydrogen going into the reaction. We have sulfate on both sides, so I'm going to write SO4. We have magnesium, and we also have hydroxides on both sides. Which means when we're counting hydrogens, let's make sure not to count this hydrogen, or rather, not count this hydrogen as hydrogen, and instead it will just be hydroxide. So now let's go through and count. There are 2 hydrogens going in, not counting these 2 because they're part of hydroxide. There's 1 sulfate going in. There's 1 magnesium and 2 hydroxides. Coming out of the reaction, we have 1 hydrogen, 1 hydroxide, 1 magnesium, and 1 sulfate. So I need more hydrogens and hydroxides on the left, and conveniently, they are both the same formula. 2 times 1 hydrogen is 2. 2 times 1 hydroxide is 2. So I can balance this by simply putting a 2 in front of the HOH. And everything else gets a 1. So 1, 1, 2, 1. Now, if you're not given the HOH, if it's not written like that, there's another way that this formula will appear. This will probably be written in the much more familiar form of H2O. This is water. And you might look at it and go, if I have H2O and MgSO4, where has my hydroxide gone? I have to do oxygen and hydrogen separate, and that's just going to screw up everything from over here. Well, the trick is to rewrite H2O as HOH. Balance it as 1 hydrogen and 1 hydroxide. Okay, let's look at another reaction. Let's do a combustion reaction this time. Okay, let's do the combustion of gasoline. So gasoline is made of a chemical called octane, and combustion means we'll combine it with oxygen and produce carbon dioxide and water. So I'm going to go through and write my formulas for everything. Now, octane is C8H18. No, you do not need to memorize that. plus oxygen is a diatomic gas. You do need to memorize that. Producing CO2 and H2O. Okay? Now, when we're balancing a combustion reaction, it's easiest to start with the carbon, then move to the hydrogen, and finish with oxygen. The reason, oxygen occurs by itself. And when oxygen occurs by itself, if we put any coefficient in front of it, it's not going to affect anything else on this side. No other element will be affected by this coefficient, which means it's not going to mess anything up by putting it there. So we'll save it for last because it'll be easiest. Let's count. We have 8 carbons, 18 hydrogens, and 2 oxygens. We have 1 carbon, 2 hydrogens, and 3 oxygens. Okay, so odd and even. That's going to be a problem, but right now we haven't balanced the carbon or the hydrogen, so let's not worry about oxygen at all yet. And let's see what it does when we balance the carbon and the hydrogen. I have 8 carbons going in, but just 1 coming out, so I'm going to put a coefficient of 8 in front of CO2. And then I update. 8 carbons, 8 times 1, and 8 times 2 oxygens is 16 oxygens. Well, now I have carbon balanced, but not hydrogen. I have 18 hydrogens going in, but just 2 coming out. So something times 2 gives me 18, that's 9. So update, 18 hydrogen. Now let's go back and look at oxygen. I have 8 times 2 is 16 oxygen, plus 9 times 1 is 9 oxygen, which brings me up to a total of 25 oxygen. Well, I've wound up with an even-odd split again. So, the easy way to do this is to divide this by 2, and I will get 12.5 oxygens and 1 octane. I can't leave it in this form though. 0.5 is a fraction that ends over 2. So I'm going to multiply it by 2, and I'm going to get 25. But if I multiply the oxygens by 2, everything else has to be multiplied by 2 or else it's not going to balance. So this 8 becomes a 16, this 9 becomes an 18, this 1 becomes a 2. Now the equation is balanced. The other way you can get rid of that even-odd split is to look for what's making it odd over here, in this case the water. You would wind up doubling, just like we did, and you would have 18 waters, and then you would wind up doubling everything else, and then just solving for oxygen. In the end, it would be exactly the same process. Okay? That's it for balancing equations. And the last one by request was, let's see, ionic versus covalent, which I've already done. So after this, I will be going through the standards and giving short summaries for everything there, just to make sure you're reviewing what you need to review. See you on the next video. If I can make this one stop.